In the last class, we were talking about basics of network theory. So, yeah, we were like seeing the basics of network theory. So, in that, we have seen Ohm's law, right? Ohm's law. The important thing in Ohm's law is you are able to hear me, right?
Yes, sir. Yes, sir.
Yeah. Ohm's law. What is Ohm's law again? Quick recap. V
Voltage
is equal to
proportional
IR under.
constant temperature and pressure.
Yes, constant physical conditions such as temperature and pressure. Okay, that is important. And the next thing is like next what we have seen something called as series and parallel circuits. When do you call two resistors in series?
Same current
The
flows.
same current flows, right? Similarly, when do you call two resistors in parallel? When do you call two resistors in parallel?
Current will be different, right?
No. See the definitions. Let's go with the definition because sometimes people analyze it differently. This is very important actually. So when you call two resistors in parallel is when see there are properties of parallel circuit. Properties of parallel circuit is current gets divided, voltage is same and all. But the definition is like something like this. Two elements are said to be in parallel when both the ends of one element are connected to both the ends of other element. When both the ends of one element are connected to both the ends of other element, then you call them as in parallel, any elements, okay? So we have seen resistors in parallel, resistors in series, voltage sources in parallel, voltage sources in series, right? Voltage and current source in series, voltage and current source in parallel. Remember all those? Then we have seen star delta voltage transformation, voltage source to current source transformation, current source to voltage source transformation. Right? We have seen all those. The, we have seen lastly what is star to delta and delta to star transformations, star to delta to star and star to delta. Right? These are different types of circuit connections. You just need to remember the formulas for this delta to star and star to delta. We have seen the what you call R delta is equal to 3 times R star, right? All these things we have seen. And what else we have seen? We have seen Wheatstone bridge, right? Wheatstone bridge circuit. What is a Wheatstone bridge? Where do we use this? When do we use this? Wheatstone bridge? Quickly. Wheatstone bridge is basically used to find an unknown resistance, value of an unknown resistance, or unknown resistor, value of the unknown resistor. There are other types of bridges which people will study in measurements basically. Okay. So these are the basics we have covered. We have seen some problems, how parallel, how series circuits are connected, right? Then we are coming to linear and non-linear elements. Linear and non-linear elements. This is important. Definitions are important because sometimes you'll get direct bits from these type of what you call definitions itself. Linear and non-linear elements. An element is said to be linear when its VI characteristics follow only one equation of straight line passing through origin for all time. This is important. Only one equation of straight line only one equation of straight line passing through origin for all time, right? And so from this there are three, A, B, and C. Okay, if you see this, is A, whether A is a linear element or non-linear element, even. See, this is origin, this is passing through origin, and this is straight line. So only one equation of straight line, this is something like this, y equal to mx, right? So only one equation of straight line passing through origin for all time. So A is a linear element. A is a linear element, right? Coming to B, B is also C, same. This is origin. This is only one equation, one straight line. Y is equal to minus mx, right? Y is equal to minus mx. And slope is negative, but still, this is a equation of a straight line passing through origin for all time. So again, this is a linear one. What about the C? C is also C. It is passing through origin, straight line equation. Okay, but this is not what you call one straight line for all time. This is not for all time. For all this negative times, it's 0. So this is non-linear element. Okay, linear and non-linear. So examples of linear elements. Examples: resistor, inductor, capacitor, linear elements. Okay, non-linear, all the voltage and current sources, all the independent sources are non-linear elements, right? Okay, remember what are linear and what are non-linear elements? All the sources, voltage source, current source, independent sources are all non-linear in nature because they don't follow VA characteristics as one straight line passing through origin for all time. Okay, you have to remember this: one straight line, one equation of straight line passing through origin for all time. Okay, next, active and passive elements. Active and passive elements. So active element is one which delivers net amount of power to the circuit, otherwise passive. What is an active element? It delivers net amount of power to the circuit. Otherwise, it is what you call an passive element. Okay. So from this, how can you see? It's like if the slope is passive, sorry, the slope is positive, it's passive element. Slope is negative, active element. Okay, slope is positive, passive element. Slope is negative, active element. Okay, see for this. Is the slope positive or negative? Slope positive, right? See, this is some x, this is some y. Y by x is slope, right? So y by x is slope, positive slope. This is passive element. For this, what is this? This is minus x. This is y. Y by minus x. Negative slope. Negative slope, active element. This is again positive slope, passive element, right? So active and passive elements. Active element is one which delivers net amount of power to the circuit. Otherwise, it is a passive element. Okay, passive elements have positive slopes. Negative elements have, sorry, negative slope. Passive elements have positive slope. Active elements have negative slope. Am I getting any? Sorry, I'm unable to see any comments. If you're, let me log in to my mobile also. Okay, this is about active and passive elements. Next, unilateral and bilateral elements. unilateral and bilateral elements. Okay, bilateral element which offers same impedance in both the directions. Okay, which offers same impedance in both the directions is called unilateral element, or which offers same impedance when direction of polarity voltage get reversed, otherwise unilateral element. So in this, if you see here, if I see the what do you call impedance or resistance, what I'll get, the slope is nothing but the resistance actually. Okay, this is y by x. Here if I take it, it's minus y by minus x. So it's the same. The impedance is the same. Impedance in the sense slope v by I is impedance or resistance for that matter. Okay, impedance is nothing but resistance in AC circuits. Okay, so when slope is same, otherwise in other terms, when slope is same, even if the direction of polarity of voltage or current gets reversed, it is called bilateral, otherwise it is unilateral. Okay, same here also. This is, if I see it, the slope is same, so this is bilateral. This is unilateral. There is slope here, there is no slope, so unilateral.
Sir, one doubt, sir.
Yeah.
In the second figure, after some time, the slope is changed to 0, right? So any
Yes.
issue for that?
No, it's same here also, right? No issue for this.
It should be symmetric, right?
Symmetric, yes.
Okay.
It should be symmetric. And also see this one. Every linear element is bilateral, but converse is not true. Why? Because of this. Okay, for linear element, you should have only one straight line equation. Okay, for linear element, as I told you, should have only one straight line equation. But here there is, the equation gets changed here, right? So even then you can call it as a bilateral. But for linear element, it should be only one straight line equation. That is why this holds good. Every linear element is bilateral, but converse is not true. Okay. Next, time variant and time invariant. This is simple. An element which is said to be time variant when its VA characteristics changes with time. See, for example, this is for T1. This one is for T1, T2, T3. For different types, the VA characteristics changes. Then this is called time variant. Time variant. If it doesn't change with time, then it is time invariant. Okay. For any element, if it changes with time, VA characteristics changes with time, then it is VA characteristics changes with time, then it is called as an time variant. Otherwise, it is changes with time. It's time variant. Otherwise, it is time invariant. So it will be time variant when its VA characteristics changes with time. Otherwise, it is it should be time invariant. Yeah, time invariant. Okay. Clear, right? It's said to be time variant when its VA characteristics changes with time, otherwise time invariant. See this. Tell me what find the nature of the following. Tell me the nature of the following. See here. This is again. I got the answers. Okay. This is a passive element, right? Passive element because the slope is positive. Slope positive. Linear element because one line, why linear element? One straight line equation passing through origin for all the time. Every linear element is a bilateral element. Every linear element is a bilateral element. If it is a linear, you don't have to check for any other thing. It's a bilateral one. Okay, here. Here, if you see, it's active. Why? Because the slope is not positive. Slope is always not positive. see, slope, whenever it is negative anywhere, it can be considered as active element. The reason behind this is, as I told you, active elements are uh, which supply power to a circuit. Sometimes, as I told you, voltage sources and current sources can be kept in a circuit such a way that instead of supplying power, they may consume power. Remember, in the last class, I told you that. The last class, I told you, in the last class, if you remember, I told you, uh, sources can be sometimes kept in a circuit in such a way that instead of taking current, they may, what you call, sorry, taking supplying power, they may supply power. See, generally independent sources supply power to the circuit. However, they can be placed in a circuit in such a way that they absorb power from the circuit. Right? This is important. Remember this. Okay. Coming back to this. That is why whenever there is any slope, negative slope, it is always an active element. Okay. Active element. Next, nonlinear. Why nonlinear again? It's not a single line straight line equation, nonlinear. Why unilateral? Slope is not same. Slope here and here is not same, right? So then it's unilateral, not bilateral. Okay. Same here. Active, nonlinear, unilateral. Same case. This is passive. Why not nonlinear? Because it's not a straight line equation here. So it's not a what you call straight line equation. It may be bilateral, but it depends upon the slope. It may become bilateral, depends upon the slope. Okay. Again, this is active, negative slope, non-linear, unilateral. Passive, why? Positive slope, non-linear, unilateral. Okay. Understood this? This is important. You may get a direct question giving the circuit. You have to find the whether it's linear, passive, bilateral, active. Okay. This type of questions may come because mostly you'll get direct questions in this. You won't be asked to do any lengthy problems. That is why it is very much possible you may get some, you may be given some diagram and you'll may be asked to comment on the nature of the circuit or nature of the element. Okay. So quickly, uh, for some practice, I want to do some questions, right? Some easy questions, which I don't think you need much of the time to do this. Find the currents I1 and I2 in this, everyone, because networks is always you have to be ready with your pen and paper, and I don't encourage you to do with your calculators. Let's try to do without the calculators. Try to find I1 and I2. Try to find I1 and I2. Everyone. And tell me the answer in the chat box. Find I1 and I2. Are you able to hear me, everyone?
Yes, yes.
Oh.
Yes, sir. Yes.
Any answers?
Sir, is
Yes.
I2 3 and I1 5?
Yes, correct. Right, everyone look here. See, the simplest way to do is apply KCL and sorry. Apply KCL at these points. Apply KCL at this point. Tell me what does KCL states? KCL states that all the current entering a node is equal to the currents leaving the node. And tell me what are the current entering the nodes? 2 amperes plus I2 is equal to 5. So I2 is 3 amperes directly, right? So these two currents is equal to 5, right? And then now I know I2 is 3 amperes. So then apply KCL here. What will be I1? So same again. Entering currents equal to leaving currents 5 amperes. Okay? Clear? 5 amperes and 3 amperes. Okay? Same. Find I1 and I2 for this circuit. Find I1 and I2 for this circuit. Is this clear, everyone?
Yes, sir.
Yeah. Find I1 and I2 for the second one. Find I1, I2 for the second one. Any answers? Quickly.
Sir, is
Yes.
I2 negative 2 or 2 in opposite direction?
Yes, it can be. Yeah. See, how do you again do this? Applying KCL. I1 5 amperes, I2 minus 2. Correct. See, again, KCL at this point. Tell me what are the incoming currents? I'll assume a direction here. This way, the incoming current is 4 amperes. This is also incoming plus 6 is equal to say some I. I is equal to 4 plus 6, 10 amperes. So 10 amperes flows from here. Again, if I take the node here, what are the incoming currents? Only 10 is equal to, at this node, is equal to leaving currents I1 plus 5. So I1 is equal to 5 amperes. Right? So similarly, coming here at this node, what are the incoming currents? I1 is equal to 7 plus I2. Right? Outgoing currents. I1 is 5. 5 is equal to 7 plus I2. So I2 is equal to minus 2 amperes. Clear? I2 is minus 2. I1 is 5 amperes. Here these are the values. Clear, everyone? Any confusion? Any doubt? Are these clear?
Yes.
Yeah. Going to the next one. So this is again a gate question. See, consider the configuration shown in the figure, which is portion of large electrical network. Okay, and again, KCL and KVLs are applicable for entire network or a part of the network. Okay, you have to remember this. It is applicable for the entire network as well as any part of the network. Okay, so consider the configuration shown in the figure, which is a portion of larger electrical network. For R1 is 1 ohms and currents I1, I4 and I5 given. Which one of the following is true? Check this. Check this. What are all given? R is given as 1 ohm. I1 is given. Okay. I1 is given. I4 is given. I1, I4 and I5. Is I5? I5 is given. So can you find I6 and I3? Can you find any of these? I6 and I3? That is not there, then C or D can be the answers. Okay. Try to find I6 or I3. Try to find I6 or I3. You're able to see the circuit, right? You're able to see the circuit, everyone?
I1, I4 and I5 are given.
Yeah, I1, I4 and I5 are given. You have to find I3 or I6. Any one of them. Given, right? I1 is 2 amperes. I4 is minus 1 ampere. I5 is minus 4 amperes.
A is the answer.
Hmm?
Is A the answer? I6 equal to 5 amperes.
Yes. See, everyone. Again, see, this is I4. I4 is given as minus 1 amp. How do I go back this? Okay, anyhow. See, this I4 is given as minus 1 ampere. Okay, I1 is given as 2 ampere. So can you find I2? I2 is, see, 2 amps is coming this way, minus 1 amp is going this way. That means 1 amp is going here. So 2 amps is coming here, 1 amp is going here. So I2 will be 1 ampere. Okay. Okay. See, I'm directly writing without applying the KCL because this is simple, right? For the first question, I have shown you with KCLs. Now you can directly think this way. 2 amps is coming this side, 1 amp is going here. So the other 1 amp should go this way. That is I2 is 1 ampere. Okay. And I5 is given as minus 4 amperes. So that means I5 is in this direction. 4 amps is going out. 1 amp is coming and 4 amp is going. So what should be this current? I3 should be in this direction. In this direction. So if this is to be 4 amperes and this is 1, this should be 3 amperes. So I3 is minus 3 amperes. So minus 3 amperes. So this is wrong, right? So I6. Now can you find I6? So minus 3 amperes or 3 amps is going this way. 2 amps is going this way. I6 is 5 amperes. Sorry. Yes, right. Okay. 5 amps is coming this side, 2 amps is going this way, 3 amps is going this way. So I6 is 5 amperes. Clear? This is how you have to write it. You don't need any calculators for this. You have to simply apply KCLs properly and do this. Okay. Okay, clear everyone? Shall we go for the next one? Any doubts? Shall I explain it again, or is it clear to everyone?
Yes, sir.
Clear, right? Yeah. Next one, see. This is a bit tougher one. If you want to try this, you can try. Otherwise, we'll go to the next one. I think this needs a bit of calculations and all. You want to try this, everyone? Or take this as a homework and try to do this. Take a screenshot of this. Everyone, take a screenshot of this and try to do this, because it involves a little bit of what you call calculations. Because this is not for gate, I don't want to do more of calculations here. You can, again, you have to find the current through 0.03 amp, sorry, 0.03 ohm resistor, which is this one. Okay, you have to find the current through 0.03 ohm resistor. Okay. A bit tricky question. If you want, I can try it. Otherwise, I'll give you some hint. Okay. So what you have to do is you have to apply KVL in this. Okay, KVL in this loop. Assume a current of I here. Okay, what will be this current? Okay, let me write down the currents. Okay, I'll write down the equation. You have to find I. Okay, this is I. Okay, let me call this as current flowing through the 0.03 ohm resistor as I. So this will be I minus 120, right? I minus 120. And this will be 70 is getting added. I minus 120 plus 70. I minus 50. Right? I minus 50 and 30 is going again. So I minus 80. And what is the current here? I minus 80 plus 80. This is I again. What is the current here? I minus 60. So again 60 is coming. It will be I again. Right? So now what you have to do? KVL in the sense, you have to, what should you do? KVL in the sense, all the drops. What is voltage drop in this resistor? Starting from, I'll call it as A, B, C, D, E, F. Starting from A, B, C, D, E, F, and A. A to B, what is the resistor? What is the voltage drop? Current into resistance, 0.03 I. 0.03 I plus what is the drop here? 0.01 into I minus 120. Okay, plus what is the drop here? 0.01 into I minus 50. Plus what is the drop here? 0.02 into I minus 80. Plus what is the drop here? I into 0.02. 0.02 I. Plus what is the drop here? 0.01 into I minus 60. Okay, is equal to 0. Find I from this. Find I from this. Understood? How to write down the equations for a circuit, KVL equations. You have to start at one point and you have to follow a closed path and come back to that point. A, B, C, D, E, F, and back to A. Okay? Okay, everyone? You can calculate it, okay? You can calculate it and find the answer. Clear? Now in the circuit, in the figure, the value of voltage source E. Find the value of voltage source E here. Do this, everyone. Try to do this. Very important question. Are you able to see the screen, everyone? I need responses.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Try to find E. Any answers? Minus 16 volts. Okay. Everyone, you have to know a few of the things. See, there is something called as ground or zero potential, earth or zero potential, you can say. So there is something called a zero potential thing. So if I say something is 10 volts, this is with respect to earth or ground. Okay, this is with respect to a zero voltage point. Okay, so if I say this is 10 volts, what is this? This is with respect to some, this is positive, and negative is with respect to a ground. Here also, if it's V1, it should be, there should be negative, which is with respect to ground. Here also, if it's V2, it should be with respect to ground. Okay. See, now I can, I have a 0 and 0. This is negative and ground is connected. So this is a closed path here. Okay, again, this ground is connected to this. Again, a closed path here. This is also, all the grounds are connected. So this is again a closed path. Again, a closed path here. Okay, you can apply KVL to any of these closed paths. Any of these closed paths. Let me apply to this one, the simplest one. You get the answer directly. Okay, this one I'm applying to this one. So tell me, in this, what do you encounter? Minus. First is minus. So this is minus 10, right? Minus 10 volts, then minus 5 volts, then minus E, then minus 1 plus 0 is equal to 0. Understood? Understood? So E is equal to minus 16 volts. Clear? Clear? See, I can apply KVL here and find V1, and then KVL here and then find V2. Then I can apply KVL here and then find E. The other way is, because in this loop I have all other values, it's easier to take this loop and find the value of E, minus 16 volts. Okay, clear? Shall I move on? You should be thorough. You should know how to write the KVL equations and KCL equations. This is as simple as that, because some questions directly one can see the question. For example, this question or the other KCL questions. These questions you can directly see the questions and tell the answers, right? So this is how you have to like prepare yourself. Okay. The next one, find the equivalent resistances. Find the equivalent resistance. This is 1, 2, 3. Three circuits. Find these. These are very important. Basics and importance. Find the equivalent resistance, everyone. See, basics are very important. You should be very clear. Yes.
Answer is 3. I guess just need to do it once more.
Answer is 3. Don't need to do much. First one. Right?
Yeah, first one.
No, not 3. Not 3 ohms. How did you say it's 3?
Actually, it's 6. I mean, 6.
You mean 6 ohms?
Yeah, 6 ohms.
Okay. See, yes, it's 6 ohms. See, the thing is, whenever you see a circuit, how to do find the equivalent resistance, you have to start from this side. You have to see what are all the series and parallel. Okay, this one, the same one is here. See, how are these three? These three are in series, right, everyone? These three are in series. So what happens now? So series 5 plus 4 plus 3, all the resistance gets added. 5 plus 4 is 9 plus 3 is 12. 12 ohms parallel with 4 ohms. How much? 12 ohms parallel with 4 ohms. It's 3 ohms. 12 into 4 by 16. It's 3 ohms. 4 3s, 4 4s. 3 ohms. Okay. So this can be replaced with 3 ohms again. 2, 1. Again 3 ohms. 6. So this entire thing will be replaced with 3 ohms. 3 and 3 are in series. So it's 6 ohms again. 6 and 6 are in parallel. It's 3 ohms again. So 3 ohms series with 2 and 1, you'll get total as 6 ohms. 6 ohms is the answer. Clear, everyone? So always you have to check, start from this side, and like if you want to find the equivalent resistance between these two terminals, you have to always start from the other end. Okay, 6 ohms is the answer. Clear? Shall I repeat? Clear, everyone? The next one. Find the equivalent resistance of this circuit. So how to find the equivalent resistance of this is called something called as infinite ladder. Infinite ladder. These are called infinite ladder circuits. So how to solve an infinite ladder circuit? Something like this. See, the logic is if you add or remove one from infinity, it's always infinity, right? So this circuit is up to infinity. So what I'll do is I'll add one more to this. Okay, so I'll add one more to this. One more branch, one more this branch. These branches are up to infinity, right? I'm adding one more branch to this. Okay, say this is RAB. So what I'm doing, I'm adding one more branch to RAB. I'll call this as RAB. Okay, 1 and 1. And again it will be RAB. Right? Is this clear to everyone? Because infinity plus 1 will always be infinity. Infinity plus 1 will always be infinity. That is why I added one more to this, will again be infinity. Now tell me what is RAB from this. These two are in parallel in series with this. So 1 is in series with 1 parallel to RAB. So this is what you'll get, 1 plus RAB by 1 plus RAB. Solve this equation, you'll get RAB plus 1 plus RAB, or 2 RAB plus 1 by 1 plus RAB. Okay, or it's 1 RAB square plus RAB. RAB square plus RAB minus 2 RAB is equal to 1. So solve this, you'll get RAB. Solve for RAB, you'll get the value. Solve it and tell me the answer. Similar one. This is also similar one. RAB 111 RAB. So this is something like this. RAB is equal to 2 plus these two are in series plus 1 parallel with RAB. 2 plus 1 parallel with RAB, solve for RAB. Okay. Okay. The solution is like main thing is the procedure is important. Okay. The procedure is important. You have to try to solve this. Everyone try to solve this. Okay. You got how to find this is also an infinite ladder. Infinite ladder circuits. This is how you have to do it. One circuit and one unknown, or one equation and one unknown. You have to do this. Ax square plus bx plus c equal to 0. Try to find this. Okay. Okay. Now again, this is this one. Everyone try to solve this. If RAB is equal, find RAB if R is equal to 300 ohms. Find RAB if R is equal to 300 ohms. Everyone find RAB if R is equal to 300 ohms. Find RAB if R is equal to 300 ohms.
Sir, can we use Wheatstone bridge concept here in the middle?
Yes, try to use that. See, anytime when you are given any circuit, you have to check for all series, parallel combinations, Wheatstone bridges, okay, all those combinations and try to solve them. Correct, 100 ohms. See, so how did you do that?
The 3 Wheatstone bridge.
Okay.
So,
Right, everyone are able to see those, right? Wheatstone bridge. Whenever you see a Wheatstone bridge, again, for those who have missed the last class, so this is something a Wheatstone bridge is. So whenever you see a Wheatstone bridge, what will you do? First thing, what will you do? Whenever you see a Wheatstone bridge, the first thing to check for is balance bridge condition, right? What is the balance bridge condition? If R1 by R2 is equal to R3 by R4, then the bridge is said to be balanced. What is balance bridge condition? When R1 by R2 is equal to R3 by R4, then this bridge is said to be in balanced condition. Okay. So whenever you see how many Wheatstone bridges you can see, this is one Wheatstone bridge. This is one Wheatstone bridge, and this is one Wheatstone bridge. Okay, and what happens under balanced bridge condition? Balanced bridge condition, what happens? The voltage at here, let me say this is C and D. The voltage at here at point C and voltage at point D are same. C and D will be at equipotentials. So equipotentials, no current flows through this resistor. So you can literally open this, right? You can open R5, or what can you do with R5? You can open the resistance R5, or what else you can do? See, when there is no current flowing through this, it's an open circuit, right? What else you can do it?
Short circuit also.
Yes. Yes. Why short circuit? Because the voltages are same at point C and point D. Zero voltage difference, or voltage is zero. That means it's a short circuit. So you can either short it or you can open it. You can either short it or you can open. Under balanced bridge condition, you can short it or open the central rim of the Wheatstone bridge. Now, see, this is the same Wheatstone bridge, but the resistance is here and this is the output. Okay, this is simply tilted, right? Simply tilted one. Okay, simply tilted one. So, sorry. So what we can do? We can remove these resistors. You can remove these resistors. So if I remove these resistors, what will be the circuit? Something like this. Sorry. Something like this. This is the circuit, right? So each of R ohms, all of R ohms. So now what you can see from this? See these two resistors, this resistor and this resistor. Let me do with another color. Yeah, black. So these two resistors, how are these two? How are these two and these two?
Parallel.
Parallel, right? See, how when do you call two resistors in parallel? When both the ends of one resistor are connected to both the ends of other resistor. Similarly, these two are in parallel, these two are in parallel, right? So all these are in parallel. So what is, if R is parallel to R, what is the resistance? Equivalent resistance? Equivalent resistance when two equal resistors are connected in parallel.
R by
R by 2, right? This is R by 2. So series, this will become 2R, right? So what happens now? This is 2R. This is R by 2 and R by 2. Again, R by 2 and R by 2. This is 2R. So 2R and 2R are in parallel. It's R again. So R by 2 series R. R by 2 R by 2 series R. So three equal resistances are in parallel. What is the equivalent resistance? Three equal resistors are in parallel. Equivalent resistance is
R by 3.
R by 3.
So R is given as 300 ohms. So R equivalent is RAB is 100 ohms. Okay. Here you can try. Yeah.
सर ये बीच वाले आर क्यों हट गए?
अभी आप join हुआ होगा. Actually, the thing is, these are all Wheatstone bridges. Wheatstone bridges. Whenever you see a Wheatstone bridge, the first thing you have to do is you have to check for a balanced bridge condition. What is a balanced bridge condition in Wheatstone bridge? Something like this. This is a Wheatstone bridge.
Yes, sir.
Okay. So R1 by R2 is R3 by R4. When this happens, you can either remove this resistor or you can short it. Okay, doesn't affect the circuit. Okay, again, the same thing, if you can repeat by shorting this, you'll get the same answer. If you want, you can try it. Okay, if you can short this, you'll get the same answer. If you want, you can try it. If you short, what happens? This two becomes in parallel, or rather, all these become in parallel. 1, 2, 3, 4, 5, 6. 6 resistors in parallel, R by 6. Okay, and here also 1, 2, 3, 4, 5, 6. 6 resistors in parallel, R by 6. These two will be in series, is R by 3. The equivalent is same, R by 3. Okay, so you can either short them or you can open them when a Wheatstone bridge balanced, when a Wheatstone bridge is balanced. Clear? Clear,
Yes,
everyone?
sir. Yes, sir. One doubt,
Mm.
sir.
Mm-hmm.
Are other bridges important in our HL exam?
Other bridges are? What other bridges?
Like we have
Actually,
heard.
yeah, the shearing bridge, all other, right? Those are important from the point of measurements. Okay, if you want to measure inductance and all, no, see, HAL, HL exam, the syllabus, they haven't given you the syllabus. Whatever they have mentioned is the syllabus will be in line with GATE. Okay, in GATE you
Okay.
have, for electrical people, it is there. All other bridges are there in measurements, not in networks, right? You have only Wheatstone bridge in networks. For all others, you'll have in what you call measurements. Okay, for triple E students. Okay, for EC students, there is no other bridges. Only you'll have, I think, this one. Instrumentation guys, again, will have all the bridges.
Sir, can you
Okay.
explain the last thing, sir? The 2R, R and R, 2R, 3, 4 resistors are in parallel, no? From there, you can explain.
This point?
Yeah, yes, sir.
Yes, yes. See here. You understood how I got the circuit?
Everything before I understood, sir.
Okay. From this, see what happens here. These two are in series, right? So this is 2R. Okay, this is 2R here. This is 2R. These two are in series. R and R in series. So R plus R is 2R. Okay, these two are in parallel. So this is
Yes.
R and R parallel is R by 2.
Yeah, this
Again,
down
these two are in parallel. What?
downside R by 2. Yeah.
Yeah, this is R by 2 again. Here
Yeah.
also R by 2. R by 2. Now R by 2 and R by 2 are in series. So this
It will
will
become
become R. R
yeah.
by 2 and R by 2 in series R. So
Yeah.
here if you see this 2R, this 2R. Okay, for simplicity I solved it here. Otherwise in the next step also you can solve. See these
Yeah.
two are in parallel, right? So both the ends of this is connected to both the ends of this. So 2R and 2R are in parallel. It's R again.
Yeah. Yes, sir.
Okay, so R and R in parallel, you'll get R by 3.
Yes, sir.
Yeah. Okay. Before that, let me give you one more question. So as in the last class, I've given something like this. What is the equivalent resistance? Quickly. In the
By
last
3.
class. R by 3, right? All these are in parallel,
By
right?
3. Yes, sir.
Clearly, both the ends of one are connected to both the ends of the others. So this is in parallel. Now, find the equivalent resistance. Find the equivalent resistance between A and B. What is the equivalent resistance now? Any answers?
R.
So how?
R,
Wheatstone bridge. Applying Wheatstone bridge.
Wheatstone bridge, sir. R by 2
Which-
and R by 2 in series.
Yes, everyone able to see it's a Wheatstone bridge, right? It's a Wheatstone bridge. It's the same circuit, right? Clear? A to C there is one resistance. A to D there is one resistance. C to D there is one resistance. C to B there is one resistance. And then B to D there is one resistance. So R equivalent or RAB is R. Okay, whenever you see a Wheatstone bridge, you have to check for balance bridge condition. And if all the resistors of the Wheatstone bridge are equal, the equivalent is R. Remember from the last class, if all the resistances of a Wheatstone bridge are equal, then the equivalent resistance is R. If you remove this, what happens? These two are in series. R and R series is 2R. 2R parallel with 2R is R. Or if you short it, R and R parallel, R and R are parallel. R by 2 plus R by 2 is R. Okay? Clear? Next. What?
No,
The
I said
current
yes.
I. What happened? Okay.
No, I said yes, sir.
No, even again, I didn't understood. What did you said something?
I said yes, sir. I said okay,
Okay.
sir.
Okay. Yeah, the current I in the 2 ohm resistor. Find the current I in the 2 ohm resistor. In the following circuit, find the current I in the 2 ohm resistor. Find the current I in the 2 ohm resistor. Two circuits, one is this and the other one is this. Find current I here, find current I here.
Right. No current or 0 ampere.
Yes, the first one is 0 amperes. Everyone right? Clear?
तो थेवेनिन इक्विवेलेंट लगा रहा हूँ तो बहुत टाइम लग रहा है सर।
किसमें?
सर आई की निकालनी है, थेवेनिन इक्विवेलेंट ड्रॉ करने में तो बहुत टाइम लग रहा है। एग्जाम के हिसाब से तो नहीं हो पाएगा।
अपने थेवेनिन इक्विवेलेंट तक चला गया। मैंने थ्योरम स्टार्ट किया ही नहीं. Okay. See, ठीक है. That's one thing. See, if you can able to see the circuit properly, it's a Wheatstone bridge again. It's again a Wheatstone bridge. So if you see a Wheatstone bridge, that's why I given it here. So these are all 1 ohms. Otherwise, I'll write this A, B, C, and D. This is A, B, C, D. Okay, what is the resistance between C and D is 2 ohms. This is I. Now can you see this? A and C के बीच में 1 ohm resistor and A and D, sorry. And A and D के बीच में 1 ohm resistor. B and C there is 1 ohm resistor, and B and D one more 1 ohm resistor. Between C and D there is a 2 ohm resistor. So whenever, again the same concept, whenever you see a Wheatstone bridge, the first thing to do is check for balanced bridge condition. Check for balanced bridge condition. Is the bridge balanced? Is this bridge balanced?
Yes.
1 by 1 is equal to 1 balanced bridge. So what happens under balanced bridge condition?
No current flows through in
No
CD.
current flows through the central limb. So I is 0 straight away.
Yeah, yes, sir.
Okay, I is 0. Okay, find I in the second one. I think the first one is clear to everyone. This is something where I think one value is missing here. This
Yes, sir.
resistor is 22 ohms, okay? Resistor is 22 ohms. So Thevenin's equivalent वो सब मत कीजिए. Try to find the current I in the circuit.
4 amperes, sir. 22 parallel, 22 final.
Yes.
That
I is not 4 amperes, but still find
Yeah,
the
yeah.
value of I. See again, everyone onto your screens. Look to your screens. 9 and 5, how are these two? How are 9 and 5? Everyone, how are 9 and 5?
Series.
Series, right? 9 series with 5 is 14 ohms,
40.
right? So 14 ohms is in parallel with 14 ohms. How much?
7.
14 parallel 14. 7. 7 ohms is in series with 11.
18.
18. 18 parallel with 18.
9.
9. 9 series with 13. 9 series with 13 is 22. 22 parallel with 22.
11.
Yes. So this, sorry, this entire will become 44 and this is 11 ohms. So the total current is 4 amps here. 4 amps. Okay. Okay. This is 22. This is 4 amps here. Okay. So if you see this, yeah, it gets equally divided. So two resistors, 22 ohms and 22 ohms. This is 4 amps. So these two resistors will divide the current equally. Remember this. Two resistors will divide current equally. So what is the current here? This is 2 amps. This is 2 amps. So now what happens again after this circuit? This 2 amps will be something like this. 2 amps. You'll have 18 ohms here and a parallel of 18 ohms. So this again gets divided equally. So this is 1 ampere and this is 1 ampere again. So I is 1 ampere. Clear?
Yes, sir.
Clear? So see, sometimes you don't need to apply theorems and all. Some questions, they are very direct. Okay. Try to do this. Use source transformation technique. Find current through resistor RL, load resistance RL. Use source transformation technique. Use source transformation technique. So what is source transformation technique? Again, for those who have missed in the last class, if I have a voltage source in series with a parallel resistor Vs and Rs, which can be transformed into current source in parallel with the resistance Rp. Okay, what will be the value of Is? Is is equal to Vs by Rs and Rp is equal to Rs. We want this way. It is current source to voltage source. It will be Vs is equal to Is into Rp. Rs is equal to Rp. Important. Use source transformation technique. Find current through resistance RL. Use source transformation technique. Current through RL. can do many other methods, but try to solve it using source transformation technique. Try to do using source transformation technique. Any answers? So how are you doing this? Okay, everyone to your screens. Everyone to your screens. Everyone to your screens. First, see this. This is a okay, source transformation technique. One more thing. These are called as practical sources. Okay, practical voltage source can be connected to a practical current source. Practical current source can be converted to a practical voltage source. Okay, ideal voltage sources and ideal current sources cannot be converted, right? So source transformation technique is used only for practical sources. What is a practical voltage source? A voltage source in parallel with a resistor. What's a practical current source? A current source in parallel with a resistor. So voltage source in series with a resistor and current source in parallel with a resistor. So this is, sorry. This is, if you see, this is a voltage source in series with a resistor. So what can I do? I can convert it into a current source in parallel with a resistor. So look at the look at the directions I'm having. This is my positive. So this is my current flow direction. So what will be the value of this current source? What will be the current source value? Vs by Rs. What is Vs here? 10 by 2. So 10 by 2 is 5 amperes. So what will be the value of this resistor? Everyone to your screens. Sorry. This is again 2 ohms, right? Rp is equal to Rs. Rp is equal to Rs. So 2 ohms again. Okay. So the other circuit is same. Okay. So now 2 ohms and 2 ohms. So mostly the mistake people do is they convert all the voltage sources into, don't convert it at the same time. Okay, don't convert them. This is how you have to do this.
Yes, sir, yes. वो ऊपर 3 वोल्ट तो जब किया ना तो बीच कंफ्यूजन क्रिएट हो गया आपके बाद वही नहीं
yes कभी ऐसा करना नहीं है. So you have to see, the ultimate aim is to simplify the circuit. Okay, if you convert all them all at a time, then you won't be able to get it. Okay, so you won't be able to simplify it. So 2 ohms and 2 ohms are in parallel. What is the resistance? 1 ohm, right? So this again is a 5 ohm. I have seen many people do this. That's why I'm telling you. So this is 5 amps and 2 ohms and 2 ohms are in parallel. You'll get a 1 ohm resistor. So again, if you see, this is 5 amperes in parallel with a 1 ohm resistor. This is a practical current source. So convert again this into a voltage source. This is how you will get, right? So what is the value of this current source? Sorry, voltage source? Is Is into Rp, 5 into 1, 5 volts. And this is 1 ohm, right? What is the remaining circuit? This is 3 volts, 2 ohms, right? Okay, the other circuit is there. Okay, just a second. I'm sorry. Yeah. Now what happened? This is how the circuit became. So 5 volts and 3 volts. How are these two series voltage sources? We have seen if two voltage sources are connected in series aiding, these are in series aiding, right? Series aiding, you'll get a what you call it? These two gets added. It's an 8-volt source, and these two are in series. 2 ohms and 1 ohm are in series is 3 ohms, right? This is how the circuit becomes. Now again convert this into a practical current source. How to convert 8 volts in series with a resistor, 3 ohm resistor. Okay, so how will you get it? Current source value is 8 by 3. Okay, and this is 3. Okay, now what happens? There is again a 2 ohm resistor here. Okay, I think I've given this as opposite. That's why it got complicated. Otherwise, it's a simple one. You'll get a 1 volt source, or like, sorry, 2 volt. Yeah. Okay, anyhow, this is how you got it. So 3 and 2 are in parallel. 3 parallel to 2 is 3 into 2, 6 by 5, 1.2, or 6 by 5, 6 by 5 in parallel with 8 by 3 amperes. Okay, so again 8 by 3, this convert this into a current voltage source again. Convert this again into a voltage source. What happens? Plus minus 8 by 3 into 5 by 6. Sorry, 6 by 5. 8 by 3 into 6 by 5. It was 16 by 5. Okay, or 3.2. 3.2 volts. And 3.2 volts in series with a resistance of value 6 by 5 or 1.2 ohms. And what else you have? A 4 volt source and a resistance of RL, 10 ohms. Now we're applying these two are in series opposing 3.2 volts and 4 volts. So the current direction will be in this way. Okay, it's 4 minus 3.2, 4 minus 3.2 by 1.2 plus 10. It is 11.2. This is what the current is. 0.8 by 11.2 amperes. Okay, you can do the math. Understood how to do this? Source transformation, you have to reduce the circuit. Series aiding, series opposing, these are important. Series aiding and series opposing, these are important. Shall I repeat or is it clear, everyone?
क्लियर सर बट एक स्टेप हम कम भी कर सकते हैं मतलब ये पे 8 और 3 आ गया ना फिर नोडल लगा सकते हैं ना यहाँ पर
Because I want to try source transformation technique में मैं बताना चाहता हूँ. That is why I'm doing this. Yes, no, अब nodal इधर से भी लगा सकते हो. That's not a point. Okay, nodal there will be a super node here and all. So I don't want to do that. That is why. Okay, I want to try it using source transformation technique because networks में any question can be any given question can be done in different ways, right? Okay, इसमें source transformation technique or what you call KCL KVL mesh analysis, loop analysis, you can do many other ways. I just want you to practice source transformation technique. Okay, next, find the effective resistance between A and B terminals. Find the effective resistance between A and B terminals. Everyone, find the effective resistance between A and B terminals. The resistance between A and B terminals, okay? R by 2, correct. How did you do it?
Wheatstone bridge.
Yes, yes. Right, if I remove this resistance here, if I remove this resistance here, you can get a Wheatstone bridge. This is something like this. Sorry for my drawing. This is something like this. Okay, this is O point, A and B. Right, this is C. Okay, so balanced Wheatstone bridge. This entire thing can be equal to R. So R parallel with R by 2. Okay. Some people might be trying this delta star transformations and all. You can do the other way also, but this is the simplest way. Okay. If you can able to see the circuit, then it's easier, simpler way to do. Okay. Anyone tried doing this inner star to delta or outer delta to star? Right? Okay. If no one, then it's good. Okay, even that also gives you the same answer. You can try converting this star to delta. Okay, you'll get the same answer. Okay, clear? Yeah, this one, if I is equal to 2 amperes, so these are all 1 ohm resistors. If I is equal to 2 amperes, find the voltage source V. Find the voltage source V. If I is equal to 2 amperes, find the voltage source V. See, everyone able to follow me, or am I going fast, slow? You are unable to follow me, right? See, the thing with the virtual classes is I can't see your faces. So whatever I get, it's through your what you call chat box and whatever you say. If you want me to slow down or if you want me to repeat anything, you can ask me. Answer for this, voltage source V. Find the value of V. Yes, 2 volts. Right? One clear how it's 2 volts? Let me redraw the circuit. If this is V, this is 1 ohm, 0.5 ohms. See, these two are in parallel. 1 ohm and 1 ohm. The current here is 2 amperes, right? So what happens now? I don't know how which method you used, whether did you use nodal mesh or node equations or any other thing. See this, these two are in parallel. So what is the equivalent resistance? These two are in parallel. What is the equivalent resistance? 0.5. Yes, 0.5 and 0.5 in series. Right, 0.5, 0.5 series, you'll get again 1 ohm. This is 2 amperes. Resistor and a voltage source. So what is the what you call property of a parallel circuit? The voltage is same. So whatever the voltage between these 2 points, it's between these two and these two. So this is 2 amps and 1 ohm. The voltage is 2 into 1, 2 volts. Okay, so the voltage source must be 2 volts. Clear? Clear? Shall I repeat?
Even simplified circuit, then 1 ohm and 1 ohm will get parallel, no, sir?
You can do that. You can further simplify it, but what's the point?
If we further simplify that point, it will get 0.5 resistance and 2 ohms as 2
No,
amperes as the current.
no. So if this is 2 ohms, what will be this this current? This will also be 2 amperes. So
Okay.
the total will be 1 ohm and 0.5 ohms and 4 amperes. Okay.
I didn't get you, sir. Can you repeat the statement again?
Okay. See, if some current I is flowing here, say for example, some I is flowing here, and this current is 2 amperes, and both the resistances are same.
Yeah.
Right? Both the resistance. If 2 amps is flowing here, what will be the current flowing here?
I minus I.
-2. And also remember, these two resistors are equal.
Yeah.
So equal resistors share current equally. If this is 2, this should also be 2.
Yes, sir.
Okay, by that logic, this will be 4 amps. 4 amps into 0.5 is 2 volts.
Yes, sir.
Okay?
Yeah, got it, sir. Yeah, got it, sir.
Okay. Next, nodal analysis. Nodal and mesh analysis. Okay, nodal and mesh analysis. Nodal analysis is nothing but KCL plus Ohm's law. Mesh analysis is nothing but KVL plus Ohm's law. Right? Nodal analysis. Select a node as a reference node. Okay, steps to determine node voltages. Select a node as a reference node. Assign voltages V1, V2 up to Vn minus 1 and the remaining n minus 1 to the remaining n minus 1 node. One node is reference node, the other is n minus 1 nodes. Sorry. Okay, assign voltages V1, V2 and so on up to Vn minus 1. The voltages are referenced with respect to the reference node. Okay, if reference node is ground, it will V1 will be with respect to ground, V2 will be with respect to ground. Next, apply KCL to each n minus 1 non-reference nodes. Use Ohm's law to express the branch currents in terms of node voltages. This is important. We will see when we do problems. Okay, solve the resulting simultaneous equations to obtain the unknown node voltages. Okay, nodal analysis as simple as this. Okay, assign node voltages to all the n minus 1 node except the reference node, and with respect to reference node, all the voltages are V1, V2 and so on. Apply KCL to all the n minus 1 nodes. Express all the branch currents in terms of node voltages. Solve the resulting simultaneous equations to obtain the node voltages. For example, this is V, R1, R2, R3, and again I'll have a resistor here. V2. Yes. again R4 and R5. So now tell me, I'll take this as a reference node. Okay, this as my reference node as 0 volts. Okay, I'll have two nodes, V1 and V2. V1 and V2. Okay. Express, so for each node you have to write down the equations, simultaneous equations. Okay, so you have two nodes here, V1 and V2. You can call this as a node, but you have, okay, you have, oh sorry, I'm having V1 and V2. I'll call them as VA and VB. Okay, okay, for better understanding, I'll call them as VA and VB. Okay, so you have to express all the node currents in terms of voltages. Remember this, all the node currents in terms of node voltages. So these all the leaving currents, take all as leaving currents for each of the node. Always remember, you can take either leaving or entering currents. Okay, taking leaving current. So tell me, what is the leaving current here at node A? I'm writing the equation for node A. Remember this. If you want, I'll explain it again, but don't get confused here. Okay, this will be for your all the networks, all the questions from nodal analysis. Okay, at node A, tell me the current equation VA, and this is the current flows in this direction. So the voltage here is V1, the voltage here is V2. Okay, this is the voltage at this node with respect to ground, V1. So the current flowing here in this direction is VA minus V1 by R1. Right? The voltage difference VA minus V1 is the voltage across this resistor, and divided by that resistance will give you the current. Plus, what is the other leaving current? This one, VA minus 0 by R2, or VA by R2. Plus the other leaving current, VA minus VB by R3. VB by R3. This is the equation is equal to 0. Understood? Understood? This is how you have to write down the node equation. Is it clear? Shall I repeat? See, for node B. Node B equation. At this, what is the leaving current? First, starting with this. What is the leaving current? VB minus V2 by R5 plus, what is the leaving current here? VB minus 0 by R4. VB minus 0 by R4 plus, what is this current, leaving current? VB minus VA by R3 is equal to 0. This is node B equation. You have two unknowns. What are the unknowns? B and A, VA and VB. Two equations and two unknowns. You can solve for VA and VB. Solve for VA and VB. Okay. Clear? How to use nodal analysis or node equations? How to write down the node equations? Clear, everyone? Clear? Am I audible?
Yes, sir.
Yes,
Clear.
sir.
Clear, right? Okay. Okay, this is what an example. Next, there is something called as concept of supernode. There is a concept called supernode concept. Okay, the supernode is formed by enclosing a dependent or independent voltage source connected between two non-reference nodes and an element connected in parallel with it, and any elements connected in parallel with it. Okay, so what is a supernode? What is a supernode? If there is a voltage source, if there is a independent voltage source, independent or a dependent voltage source between two non-reference nodes, and that is considered to be a supernode. Okay, how to write the equation for a supernode? I'll explain it. Okay, what is a supernode? A supernode is formed when voltage source, independent or dependent, is connected between two non-reference nodes. Okay, any resistance in parallel with this, any resistor or any element in parallel with it can be considered, and it will completely be a supernode. Okay. So how to write the supernode equation? So this is a voltage source. If you see here, this is a supernode. A voltage source is connected between two non-reference nodes. This is my reference. Okay, two non-reference nodes. I'm having a voltage source. How do I write a supernode equation? Look here. So for writing currents at A, okay, tell me at node A, these are all the leaving currents. Okay, and this voltage is V1, and this for B, these are the leaving currents. Okay, now tell me at node A, equation for node A. Okay, node A equation is, what is this leaving current? Anyone?
V1 minus
VA minus V1 by R1.
R1. Next, plus
VA by R2
VA by R2. Next,
VA
प्लस एक डमी वेरिएबल I ले लेंगे.
नहीं, सुपर नोड में क्या करेंगे कि will ignore this voltage source. Okay, continue writing the equation at this.
minus VB by
Yes, VB by R3, VB by R3. Tell me at this node, plus VB minus V1 by R4 is equal to 0. This is one equation. Clear? Understood? Shall I repeat? If there is a voltage source independent or dependent between two non-reference nodes, what will we do? We'll simply write down the node equation without considering this. Okay, we'll combine these two nodes. We'll combine these two nodes and write down a equation for this. Okay, this is equation 1. What will be the other equation? Can anyone tell me?
VA minus VB plus
VB
VB.
minus
VA minus VB equal to VS. Okay, or I can write it C here. This is how it is, VS and VB. For all those who gets confused, this is my VA. VB. See, whenever I say VA or voltage, some voltage, that is with reference to ground, right? So this is my VA and VB. So this is how it is, plus minus, plus minus. So write down the case KVL for this, minus VA plus VS plus VB is equal to 0. So what is VS? VS equal to VA minus VB. Clear? Two unknowns, two equations. Solve for VA and VB. Clear? Clear about the concept of supernode?
Sir, actually, how can we combine these two equations? Any special reason for that?
No special reason. There is no special reason actually, because what happens is if I know the volt. See, these two are non-reference nodes, right? If I say VA with respect to B, this voltage I can't define it because VA is defined with respect to ground, VB is defined with respect to ground. Right, that is why what we do is VA minus VB is VS, or VB minus VS depends upon the polarity of VS. That is how we do it. Okay, and one more thing you have to observe is, even I told you any elements connected in parallel with it. If I have a resistor in parallel with it, what happens? What happens to the voltage across the resistor? It will again be Vs. Property of parallel elements. The voltages will be same. So that is why I can ignore all the resistances connected in parallel with the Vs. Okay.
Okay.
Yeah. So you have two equations and two unknowns. You can solve for VA and VB.
I got one doubt here. Why
Yes.
can't VB minus VS are? Second equation.
That's why I wrote it. So this is my VA with respect to ground. This potential is VA. This potential is VB with respect to ground. Write down the KVL for this. Starting from this, you will get minus VA. The first sign you encounter, minus VA. First sign you encounter, plus VS. First sign you encounter, plus VB is equal to 0. Closed path KVL. So from this, VS is equal to minus VA. You'll get plus VA minus VB.
Yeah, okay.
Depends upon the polarity of the source, Vs, or the polarity of the voltage source.
Yeah, okay. Yeah, got it, sir. Hello, sir.
Sir, you're not audible.
Hello? Now? Am I audible now?
Yes,
Yes, sir.
yes, sir.
Yes, sir.
Okay,
Yes,
thank
sir.
you. Okay, okay. I think there was some network problem. Now coming to mesh analysis. Is it clear? Super node and nodal analysis? Nodal analysis and super node. Concept of super node and nodal analysis. Okay. Now we will see mesh analysis. Again, steps to determine mesh currents. Assign mesh currents I1, I2, up to IN for all the n meshes. Okay. Apply KVL to each of the n meshes. Use Ohm's law to express voltages in terms of mesh currents. Important. Use Ohm's law to express voltages in terms of mesh currents. In nodal analysis, currents in terms of voltages, branch currents in terms of voltages. Here, voltages in terms of mesh currents. Okay. Branch voltages, sorry, currents in terms of branch voltages or voltages in terms of mesh currents in here. Okay. Solve the resulting n simultaneous equations to get the mesh currents. Okay. See again. So you have two mesh here. So I have two equations, I1 and I2. Yeah. For first mesh and second mesh, two meshes. Okay. So mesh 1, I'm writing the equation for mesh 1. Everyone, see, whenever you follow, you have to use only one direction for not confused. Someone uses I1 in this, some uses the in the other way. I always try to use it in clockwise. You can use counterclockwise directions. One in clockwise, one in counterclockwise. Only thing is you should not get confused. Okay, that's the thing. It's always better to follow one nomenclature. I always use clockwise currents. It's better to do this, or I got habituated. So starting from A, B, E, F, and A. Starting to A, B, E, F, and back to E. Write down the voltages, equation of voltages. So what is the voltage drop between A and B? Current is I1 into R1. I1 R1 plus what is the voltage drop in R3? The current here is, this is I1 and this is I2. So it is I1 minus I2 going clockwise direction. So I1 minus I2 into R3 or R3 into I1 minus I2 plus or minus, I'm encountering minus. So this is minus V is equal to 0. Okay. This is equation 1. Equation 1. Next, mesh 2. Mesh 2 starting from B, C, D, E, and B. B, C, D, E, and B. So starting from B to C, what is the resistance? R2 into I2. So I2 into R2 plus I2 into R4 plus what is the current here? I2 minus I1 into R3 or R3 into I2 minus I1 is equal to 0. Equation 2. Here?
Yes.
Okay, this is how you write down the mesh equations. Or else what you can do is for any mesh, see this is mesh 1, right? Mesh 1, what are the resistances? R1 and R3. So I1 into R1 plus R3. Okay, this is voltage, and always see if the current I1 and voltages are in the same direction, it's V is equal to I1 into R1 plus R3 minus the other current, which is in the opposite direction, into this what you call common resistance, I2 into R3. It's the same thing. Okay, the other equation, all the resistances in the mesh, R2, R4 and R3. So I2 into R2 plus R3 plus R4 minus I1 into the common one, R3, is equal to 0. You can write it this way. Yes. Someone raise the hand. Is it clear? What I did is both the same, both are same. I2 R2, I2 R3, I2 R4. See, I2 R2, I2 R4 and I2 R3 minus I1 R3 is equal to 0. Similarly, all the resistances in this mesh is R1 and R3 into I1 minus the current in the other mesh, minus I2 into a common resistance R3 is equal to V. Okay, clear? Clear? Again, am I audible?
Yes, sir. Clear.
Okay. Next concept of super mesh. Again, what is super node? If there is a voltage source between two nodes, it's a super node. What is a super mesh? Super mesh results when two meshes have a common current source, dependent or independent common current source. Okay. Common current source. And as I told, in case of super node, voltage source and any parallel element, right? So if it's current source, it is series element. Okay. Voltage source and parallel element. Why current source and series? Because in series, whatever the current flows through that series resistor, the same current will flow through the what you call current source, or whatever the current source, current through the current source, the same value will be into the resistor. Okay. Example. I'm sorry. Similar one. Okay. So now how to write down the equation, everyone. So this is my I1, this is my I2. Tell me the equation. Tell me the equation.
I1 R1, I2 R2, plus V2 minus V.
Yeah, I1 R1. Sorry, I1 R1 plus I2 R2 plus V2 minus V1 is equal to 0. This is equation 1. Ignore this and write down the equation for the entire loop. Okay. Next, what will be the super node equation? Sorry, super mesh equation. Super mesh equation will be current here. This is I1 and this is I2. What will be I? I will be, or what are the entering currents here? Entering currents is I plus I1 is equal to leaving current I2, or I is equal to I2 minus I. Okay. So two unknowns and two equations, solve for I1 and I2. Clear? Concept of super mesh. Now if there is any resistor here, nothing. You don't have to consider the value of the resistor also. Okay. Because whatever the current I here, this current source forces the same current to flow through this resistor, irrespective of the value of resistor. Okay. Clear? Clear with the concept of super mesh?
Clear.
Anyone?
Yes, sir.
Clear, na? Now find the voltages at nodes V1 and 2. Let's do 2 or 3 problems. Shall we continue? It's 10:30. If you want, we will do 2 or 3 problems, small problems, direct problems, and we can stop. Otherwise, if you want, I can stop. You wanna do it? Find the voltages at nodes 1 and 2 quickly. Find the voltages at 1 and 2. So how do you do this? Which method?
Nodal analysis.
Yes. Write down the equations for V1 and V2. Write down the equations for V1 and V2. See, what I'll do is I'll write down the equations. Everyone to your screens. See, always take the leaving currents. Always take the leaving currents at both the nodes. Okay, tell me at node 1. Node 1, what are the leaving currents? -1 plus V1 by 2 plus V1 minus V2 by 6 is equal to 0. Okay, clear? Node 2. Tell me the equation at node 2. Everyone, tell me the equation at node 2.
4 plus V2 by 7 plus
Sorry.
2 minus V1 by 6.
So leaving currents is 4, yes, plus V2 by 7 plus V2 minus V1 by 6 is equal to 0. Okay, solve for V1 and V2. Okay, you have, I'm just giving you how to write down the nodal equations. Is it clear? Nodal equation? Clear?
Clear.
Yeah. Next one. Find V and I. Find V and I. Find the value of V. V is the voltage across this. Current is, I is the current through the 2 ohm resistor. Find V and I. How do you do this? Again, nodal analysis. Okay, V1 and V2. Okay. Write down the nodal analysis, node equation at these two, V1 and V2. Did anyone see a supernode here?
Yes.
Yes, right? Tell me the equation. Tell me the equation.
So V1 minus 21 by 4.
V1 minus 21 by 4. Then
V1 by 3
V1 by 3. Then
plus V2 by 2.
V2 by 2 and V2 by 6 is
6.
0. What is the supernode equation?
V2 minus V1 equals to 9.
V2 minus V1 is equal to 9 volts. Okay. So solve these two for V1 and V2. You'll get V is equal to V1 and I is V2 by 2. Okay. Everyone clear how to write down the equations? Solution is simple. Writing the equations is important. Clear? Shall I move on to the next one?
Clear.
Now find the mesh currents I1 and I2. Find the mesh currents I1 and I2. Mesh 1. Tell me the mesh current I1 and like the mesh current I1. Tell me this. See, as I told you, it's like I1 is I1 into all the resistances. Add all the resistance. 12 plus 4 plus 2. It's 18. Right? I'm writing directly. 36 is equal to 18 I1 minus 12 I2. Equation 1. What will be the second equation? Mesh 2. Mesh 2 is minus 24 is equal to 9 plus 3 plus 12. 12 plus 12, 24 I2 minus 12 I1. Clear? Shall I repeat? Clear, everyone? What did I do? I added all the resistors in this mesh. 2 plus 12 plus 4 is 18. 18 into the mesh current I1. And what about the common one? 12 into the minus of I2. Okay, it's in the opposite direction. 12 into minus of I2. And this is going in minus 36. In this direction, minus 36. So minus 36 is equal to plus 36. Okay, here what happens? It is plus 24. So is equal to minus 24. And all the resistances 12 plus 9 plus 3 is 24. 24 I2. And then the common one is 12. 12 into I1. Minus 12 into I1 is the second equation. Clear? Clear, everyone?
Clear. Clear.
Clear, right? You can solve for I1 and I2. This one, quickly. Find the mesh currents I1, I2 and I3. See, I don't know, am I going fast or are you able to catch me? Or shall I stop here and continue in the next class? See, for the mesh 1, tell me the equation of mesh 1. Do you see any super mesh? Anyone super mesh?
Yes, sir.
3 ampere.
Yes, there is a super mesh here, right? So tell me minus 6 plus 2 into what is the current flowing here? I1 minus I3, right? Then directly coming here, see super mesh, there is a current source in series with resistor. You can ignore this one. Okay, then plus 4 into what is the current here flowing to this I2 minus I3. Everyone tell me, then plus
8i2.
8I2 is equal to 0. Equation 1. What is the second equation? Super mesh equation. Super mesh equation. Tell me the super mesh equation.
Minus 6.
Minus 6. See, super mesh equation is the current.
No.
Yeah. See, the current here is, if you see the current here. Okay. This is my 3 amps here. Everyone see this. The current here is I1. Okay. The current here is I2. Now tell me what is the super mesh equation?
I1 minus I2 equals to 3.
Yes. I1 minus I2 is equal to 3 amps is the super mesh equation. The third equation is mesh 3. Mesh 3 equation is again 4 plus 2 plus 2, 8 into I3. 8 into I3 minus 4I2 minus 2I1 is equal to 0. Okay. 3 equations, 3 unknowns. Solve for I1, I2 and I3. Okay. Clear, everyone? Clear? Shall I repeat?
Sir, clear.
Clear, na? That's for today. Okay, I want you to practice more because the thing with networks is if you're clear with the basics, the rest will simply follow. Okay, the rest will simply follow. So we are down 2 classes and I think I covered basics, mesh analysis, nodal analysis, super mesh and super node. If this is for gate, I would have solved some more difficult questions and some more numerics. And I don't know, I don't think that those are important for you because you won't be given any calculators or anything as such. So this is enough. Okay. Okay, you can practice more. If you get doubts, you can ask me anytime. Yeah, I will available on WhatsApp also. Okay. Here, this is for today. Okay. Okay, and closing.
Thank you, sir.
Thank you.
Thank you.